Hello, my friends. Welcome back. In the previous videos, we talked about regression and we also covered the linear regression. In today's video, however, I'm going to show you how we can use the nonlinear regression models. So we talked about this slide, this one and this one as well. And now let's talk about the nonlinear regression models. Okay, so the first nonlinear regression model is the polynomial, right? As you can see, it looks very much like the linear regression model. You can obviously have simple or multiple. The example that you see here is multiple because we are using more than one input features. It's x1 and x2. But what makes it polynomial is that like you have higher orders of magnitude here. You're like, okay, I have the second degree terms here, x1 to x1 squared, right? x2 squared. And then like you can have power of 3, power of 4, and so on and so forth, right? So as you can see, it's still like very much like the linear model. And I will show you in a few minutes when I actually start coding in Python that Python also treats this as a linear model, right? So you have to do something. You have to do some pre-processing on your data to transform your data and everything. But at the end of the day, this is still not a linear regression because basically what happens is that Python says, okay, I have x3, for example, and I can say x3 equals x1 squared, right? Something like this. Then I can rewrite this and be like, okay, this is c x3. You see, that's why they say, okay, it's still in quotes a linear model, but don't let that confuse you. We'll see how we can do that in Python in a few minutes. But yeah, this is the polynomial. And then we have the actual nonlinear models. And you see it doesn't look anything like the previous models. You have like a division here. You have log function. You can have exponential. You can say like e to the power of x3 or something like that, right? And so on and so forth. So these are the nonlinear model. What happens when it comes to nonlinear model is that Python cannot really choose a model for you when you say, okay, I want to do like a linear model. Python knows, okay, linear is this, right? Some coefficients, an intercept, stuff like that. But when it comes to nonlinear model, Python says, okay, give me a model. So you, as a designer, have to come up with an idea of what the model is going to look like. So the first step is that you have to plot the data and look at the data based on the experience, based on your knowledge. You'd be like, okay, this data looks like this function to me. And then you define that function and use Python to train the function and, do some measurements, predict, get the accuracy, stuff like that. But again, we will see all that in a second when we start coding in Python. But again, at the end of the day, the purpose of all these machine learning algorithms is that you want to increase the accuracy while still keeping it simple most of the time, right? You want to come up with an idea, be like, okay, I tried a linear model, the accuracy was like 70%. I don't know, moved up to a polynomial, and then the accuracy jumped up to 80%. And now I used a nonlinear model, and now I have like 95% accuracy. That's probably what we want. Anyway, let's start coding in Python. And now that we covered the basic math behind it. Okay, have my Python project open here. So it's very similar to what we did in the previous session. So let's just go import numpy as np. Import pandas as pd. What's going on? As pd, and import matplotlib.pyplot as plt. Okay. So just like before, I'm going to use the same data set as before. So let's open our data set. Our data frame or data set, whatever you call that, is pd.read CSV. And it was co2.csv. And let's just say print df dot columns. Wait, that's not what I printed. df dot columns. Okay. And if we run this now, it says, okay, here are the columns. You remember the data frame from before. It's the CO2 emission data set. So yeah, we have the make, model, class, engine size, cylinders, blah 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 in the data frame. All good. Now we can move on. Just delete that. Just like before, I'm just gonna define the selected features here. That's equal data frame of let's choose this one. I'm gonna bring it up here. What else? So we did the number of cylinders. Let's do that again. That's good. We can go, for example, fuel consumption combined, highway and the city. That also goes there. And finally, the CO2 emission. That's the thing that we care the most about. We want to predict this. Okay, so we have this. Just like before, I'm going to divide, like split my data into train and test with the 80% rule that I told you. So we go, we define our masks just like before, np that random that rand, how many, it's len of our data frame, and if it's less than 0.8. So it gives me roughly 80% of the data frame true and like 20% false. And I'm gonna go, my train set is selected features where mask is true, right? And then my test is selected features where mask is not true. Okay. And now let's prepare data, right? So I'm just gonna go train X, right? That equals numpy as any array, and it's train of engine size. Let's just bring this guy over here. Okay. For now, we can keep this, simple linear model, not multiple. We usually just one input feature, but we can later add as many as we want. And then train Y, which is the labels that we want to train based on. It's numpy as any array. And it's from train. And that's CO2 emission. Okay, let's just bring this guy over here as well. And then we obviously need to do the same for tests. So let's just copy that thing, put it here. This will be test. This is also test. Oops, what's happening? Just select this and then go test. And then this would be test X. And these are going to be our test labels. Okay, so far so good. We haven't done anything new here yet. Now let's add something to it that makes it different, and we want to use the polynomial for now. So I'm just going to go from scikit-learn dot pre-processing import polynomial features, right? Just one quick note here. It's not a good practice to have the import statements in the middle of the code, right? You have to, well, you don't really have to, but it's good practice to put them all up here, right? But for the sake of this video, I'm just going to keep them here so that you will see as we go what's happening. So I'm just going to add that, and then I'm going to go poly equals polynomial features and degree equals 2. So I just want to go to the second degree. Second degree is input features to the power of 0, to the power of 1, and to the power of 2. So that's like the highest power that we have in our polynomial. You can increase that to as many as you want. But again, like just keep it like this. And so what it does is that it says, okay, I want to use a polynomial of degree 2. Okay, let's see how we can do that now, how we can use that. Now I can go train x poly, right? We had the train x here, which was the arrays before we were using it. But now I want to use polynomial, so I have to transform my data. So I'm going to define this train x poly that equals poly, the feature, the object that we have here, dot fit transform. So it's transforming the data and it's getting train x for that purpose. So it gets train x, right, and brings it to this second degree polynomial format. If it's confusing, let's see what our data looks like now. If I go print train x, not all of them, just the first three, and then print train x poly, not the whole thing, I just want this part, train x poly, also only the first three. I just want to see how we transform the data, right? So let's clear this in here and run this. And it says that, let's just give it a few minutes. Okay. It says that the first train x, like the first value for the feature in your train, you see it's the engine size, right? In my train x. And it says the first one is 2, and then 2.4, and then 1.5. Okay, good. These are from my data set. Haven't done anything here yet. But now, if I transform the data, right, and bring it into this second degree polynomial format, what's going to happen is that it's going to give me this. What is this? That's exactly what I told you. So if we want to do this, this is like x to power of 2 plus x to power of 1, which is basically x, plus x to power of 0. This is what it does, right? So x to power of 0 is always 1. That's where you can see. So 2 to power of 0, that's 1. 2.4 to power of 0, that's 1. 1.5 to power of 0, that's 1. The second one is x to power of 1, which is basically the same input. So you see 2, 2.4, 1.5. And the third column in here, that's the squared of inputs, right? So 2, that goes to 4. 2.4, that goes to 5.76. And 1.5 to the power of 2, that's 2.25. So this is like basically transforming our data. And that's what I meant when I was talking in this slide, that, okay, it takes this and assigns a new variable to it. And it says, okay, that's like my x2 or x3 or something like that. Like it defines a new variable basically. And it says, okay, now I have, like, instead of 1 data, now I have 3 data, and I'm going to use these to learn something, right? Okay, so hopefully that's clear. If not, just listen to what I said a few more times until it makes it clear, but it should be straightforward now. So far so good. Now we have like our data transform, and now we're ready to learn the model. This is where the fun begins, right? I'm just gonna go from scikit-learn, right? Import linear models, just like before, right? That's what I told you. Like, polynomials are something like they're not really linear, but at the same time, they are not non-linear as well, right? If that makes even sense. But let's do this. We do the exact same thing that we did before. Regression is linear model dot. I'm just gonna use a linear regression, and I'm just gonna go train y. These are the values that we are guessing. So that's regression dot fit. This is the chain model, right? And now we just use the transform data to train, right? And the training labels or train Y. So this is like how we train the model using the transform data that we did here. And now we can actually see the coefficients and the intercept and everything just like before. So if I'm gonna go coefficients, hopefully I didn't make a typo there. That's regression the coef and print intercept, which is regression dot intercept, right? We can do this, and let's clear this. And it says, just give it a few seconds. It says, okay, fair. Okay, that's not FIR. That's fit. Okay, clear. It actually says like did you mean fit? Like it's important for you to learn how to read the errors. So let's see. If I run that again, what's gonna happen is that it says, okay, so these are the coefficients 0, this, and this. Sometimes the model is just very easy that it says, okay, I don't really need like one of these coefficients, right? Because it comes up with A this, B times that, and C times this. Sometimes it says, this model is like too easy. I don't, for example, need the squared model, depending on the data set that you're using. But again, like you can see the coefficients here, you can see the intercept, and then obviously I can go just like what we did before, right? I can go from cycle where the metrics, import R2 score, and then I can go test X poly. Now I want to see the accuracy of my model, right? I'm just going to go poly that fit transform test X, right? I want to transform my X data, and then I'm just going to go test Y underscore, which is the predicted values, is regression dot predict test X poly. So get the test values and give it a prediction result. And then I'm just going to go print. You can do the MSE as well. Well, let's actually do that. So MSE is numpy dot mean of something, right? And that something is test Y, which is the actual value, minus test Y underscore, which is predicted value. We need to square that. So that's that. And then print R2 score. That's also equal to R2 score of test Y and test Y underscore. So if we print those, let's see what's going to happen here. It says, okay, so the MSE is almost 900 and R2 score is 0.73. I don't remember exactly what the R2 score was for a linear model, but this is at like 7.73. We can try adding, I don't know, like more input features to see if that makes it any better. I'm just going to add these two features here. Obviously, they go here as well. And so these are what we have, 900 and 0.73. If I run that now, hopefully that improves the accuracy. Wow, it does. So the MSE, mean square error, it drops from 900 to 276, which is a huge improvement. And our R2 score goes from 0.73 to 0.91, which is amazing. Which means, okay, we have a good working model. That's good, perfect. So this was about the polynomial. How we covered the, like, you can actually increase the degree here and see what happens. But we saw the simple, the multiple polynomial regression models, and we should be good to go now with this. Now actually let's move on to the other model, the nonlinear model, the actual nonlinear model. I'm gonna delete all these. Hopefully we're not gonna need them. And I just want to clear that. And okay, let's actually start with the nonlinear model. So for this data set, the CO2 data set, that was easy. Like we could get R2 score of 0.91 and with only like linear or polynomial models. Now I want to use a different data set. It's the China GDP. It's again like a data set from the Kaggle website. I'll make sure that I put a link to where you can download this data set. But what's happening here? Let's see. If I go, let's see how a data set looks like. Go df that head, give me the first 3 rows of my data and see what happens. If I run this, it says your data set is something like this. It's the year and the value, the GDP value, the gross domestic something, I forgot. Anyway, but like that's basically shows like the growth value of the economic of the countries. But it says in 1960 it was this much, in 1961 it was this much, and so on and so forth. If I plot that, let's actually plot that. So I'm just gonna go my x data equals, let's do it this way, x data y data, that's equal, it's a tuple of data frame, so it's year, right? So with capital Y, that goes here. So get that column, but I don't want the column like the header of the column, so that's why I go that dot values. It just returns the values of that column for me. And then the second data, which is the year, oh sorry, it's the values, it's gonna be df of this value. Just copy that, bring it over. So that dot values. So do not confuse this value with this value. This is the header name, like the name of the column, and these are like the feature, like get the values for me. And let's plot the data. If I go plt.scatter x data and y data, I can go plt.x label. The x label is year, so I'm just gonna put year in here, and plt.y label, that's the value, right? And then plot the show, obviously, to see the result. And let's run this now. If I run this, it's gonna give me this plot, and it says, okay, like since 1960 to this year, whatever this year is, like you can go here and it's looking in 2014. This is like how the GDP values changed, right? And you look at the data and you're like, well, there is no single line that I can assign to this. Like these changes here are just, they don't look like a line. Okay, so I cannot really use the linear regression or the polynomial here. Okay, what am I supposed to do? You still can, like you can assign a line like goes from here to here, for example, and then you can see how good or how bad it performs. But just looking at the data, you're like, okay, the linear is not the best option. I have to go with the nonlinear model. So now that you have to come up with a nonlinear model, this all now depends on your experience and your knowledge. So you look at this and I'm like, this to me looks like a sigmoid function, right? If you don't know what a sigmoid function is, don't worry about it. We can learn that together. So let's see. If I go, what's happening here? If I go x equals numpy dot array range from -5 to 5 with step size of 0.1, and then go y equals 1 over 1 plus np dot exponential of minus x. This is the function that I just boosted. This is a function. Just for a second, forget about this, whole data set and how it looked. I want to talk about the sigmoid function for now. I'm just like saying, okay, my x values, they go from -5 to 5 with this step size. So the first data is -5. The other one is -4.5, -4.8, and so on and so forth. And for each x value, this is the y. Y equals 1 over 1 plus e to power of minus x, right? It's a numpy. That's what we have, numpy.exv exponential. Now that we have this, we can plot the data. We can go plot x and y and plot.show. Let's see what's going to happen if I do this. It says, okay, it's something like this. Amazing. This is kind of looked like what we had, right? Like if you remember, we had like data is coming from here all the way up here. So it looks like this. So I'm like, okay, like the general behavior of this plot looks like that. Let me see if I can make it closer to that. If I go, I don't know, -2 times x, right? And see what happens here. If I do this, okay, it's like not as around anymore. It's not as smooth. It's just like deal of this, which is an interesting thing to do, right? It's like, okay, it's around 0 still, just like before, but it looks like it's like more straight up, like the steepness here changed. We can verify that if I change that to 20, for example, and replot that. It's basically like square, like a step line. It goes here and then jumps up here. So with this parameter, you can define the steepness of your diagram. But let's change that to 10, for example. And then I'm saying, okay, what is it centered around 0? If I go -2, for example, does it change anything? And I look at the data and says, oh, it moved the center towards 2. So this is how I can shift my data to wherever I want. And then I can plot this and change the steepness with the other factor. So visually, when you look at it, you're like, okay, yeah, I can see how we can like map something like this to the data set that we just saw, right? So this is what I'm going to do exactly. I'm going to define a sigmoid function, sigmoid, and it's going to get an x value. It's going to get b1 and b2 is the parameters that we just saw. And then we can say y equals, just going to bring this thing over, right? And we don't really need these anymore, so let's just get rid of these. So y equals 1 over 1 plus numpy exponential minus b1 times x, that's lowercase x, minus b2. So this is a function that I define, and I'm just going to go return y. So far, still good fit. Let's just delete these. Don't worry about them. Yeah, let's just delete them so that we have like more room. We can see what's happening here. So this is my sigmoid function. And then let's see what happens. If I go just like randomly come up with something, say B1 is 0.1, right? And B2, that was the years going from 1960, we saw in the data set, to 2014. So I'm just going to go randomly like 1990. Uh, and then I'm just gonna go the prediction values are sigma weight of X data, right? I'm just gonna give my X data to this guy with this B1 and B2, right? And I'm gonna go plot, let's just like plot something to see how bad or how good our data look. So I'm just gonna go plot X data, Y data, right? Or let's just do this. Y, the prediction values that I had, and then I want to plot X data versus Y data, which is like the actual value that I had, and I want to do that in like red and big like O's or dots or circles or whatever you want to call them, and I just want to show them to see how bad my model is or how good it is. I don't know. I just randomly pick the parameters. So if I do this now, what it's gonna give me is something like this, right? It says, your data is something like this, and the predicted value is this, which is like very bad. And you see, because like these numbers are like really, really high here, so I have to come up with some better values to fix this. And this is where Python comes in, right? I'm like, okay, so let's see what I can do now. If I go change something here, right? Let's do something. A very common thing that data scientists do, it's called data normalization. So what it does is that it gets the X data and it says that the previous X data had divided by max of X data. So they choose the biggest value in the input data and divide everything by that value. So this guarantees that the new X data values, like these guys, are always, always, always between 0 and 1, right? Or if you have negative inputs, -1 and 1. But the range is limited, so you know exactly what you're dealing with. It can do the same thing for Y data, right? So Y data equals Y data divided by max of Y data. And now actually let's start training our model. So this was called the normalization process. Again, I'm just calling an import function. I'm importing something here, but good practice is to do it at the beginning of the file. So I'm just gonna go from SciPy, that's a new library that we're using, that optimize. Have I, yeah, should be good. From scipy.optimize. If you haven't installed SciPy, go ahead and install it. So from that, import curve fit. Yes. So the curve fit is basically what it does is that it keeps playing with these values to find something that perfectly matches the data that we have, right? So when I import that, I can go parameter optimized, right? Just the name, optimized parameters or whatever we want. And it returns like, okay, you can actually look at this function, right? To see, like, read the documentation to see what it returns. This is supposed to be an advanced course, so you're supposed to start learning about reading the documentations yourself. So just like take a look at this function and see what it returns. But it returns two values. The first one is the optimized parameters, and then the second one is the covariance of the parameters, right? Like pcov, let's say, for the covariance. We're not going to really use this function. If you're not using it, you can just like call it underscore. Like, I don't care what it is. But for now, I'm just going to keep it like that. And that's curve fit of the function that I define is the sigmoid, right? So I'm saying curve sigmoid, the function that I had with X data and Y data, right? And then once you're done, print F. I'm just going to go B1 equals permanent optimized or p-opt 0, right? Because it has b1 and b2 in there, right? So that and b2 equals p-opt 1, right? And let's see if I run this now, just to make sure everything works and nothing is broken. It did something and it says, okay, B1 is 690 and B2 is 0.99. Okay, we have the values that we want. Now let's go ahead and plot it, right? Now I want to go x equals numpy dot line space. This is also like something cool that we're going to learn. So from 1960 to 2015, right, give me 55 points. This is what it does. You like, okay, I don't know the exact step size. I don't care. I just want 55 points within that range, or 60 or whatever number of points you want, right? And I'm going to go x equals x divided by max x, right? So I'm normalizing my x value, and y equals sigmoid of x. Okay, that's also good. And now I can go plot. I just want to see how it looks. X data, right? Y data. And I want to see that because these are the actual values, like actual normalized values. These are not the predicted ones. I'm going to show them with red circles, and I'm going to label that as data, like the actual data. And then I want to plot X and Y, right? With label goes like this is the fitted values. Like the plot function, it has like a lot of different features. Like label is something we just saw. We didn't see that in the previous videos. The other thing is, I think it was line width, that you can actually give it a line width, like how thick of a line it used to plot data. And so you can go plot the bar label that's GDP, and plot that X label that's obviously year, and plot that show. Okay, let's see what it looks like. If I plot that sigmoid X, it's not happy with the sigmoid function in line 30, right? It says, okay, I don't really know what the sigmoid is here that you're calling, so you need to do something about this. So what I'm gonna do is that, yes, sigmoid, as you remember, it had 3 inputs. We also need to grow at B1 and B2. But we calculate them here. So I'm just going to go sigmoid that and star this, which means like bring everything in here. Instead of going p-op 0 and p-op 1, I'm just going to go star p-op, which means like bring everything over. And let's try that again. And it says, okay, like this is the line that I came up with. The GDP values are this, and this is the year. And this is like how it looks, right? Really cool, amazing. Which is like very close. Then what you can do now is to, I'm not gonna do this, like this can be really good practice for you, that to plot, to measure the MSE and R2 score to see how good of a fit you have. But visually looking at it, it says, oh, it's good, like it's decent. I'm following the actual data. Sure, yeah, the error here is not the best, but by other than that, everything is like pretty close, I would say. So try to do that using the R2 score, or I don't know, the MSE metric or something like that. The other thing that I want you to do is that we've normalized the data. Now our years are from 0.97 to 1, but the actual data that we had was from like 1960 to 2015, right? So this is not really normalized. And also the GDP values, right? This is also normalized now. What you can do, like a really good practice for you, is to see how you can denormalize the model that you have, right? And plot it versus the actual data and see how good that looks there. Do that and let me know in the comments what you came up with. And as always, thank you for watching me and hope you have a good one. Take care. See you in the next video. And before you go, don't forget to subscribe so you won't miss our videos. Thank you again. Have a good one. Take care. Bye-bye.